This is all the electrics in the Hammond and Morgan controller for the model railway. I needed casing only, so I removed all the internals. But I think it would be interesting to analyze what's inside. It's a little bit of a nightmare from the modern electrical safety point of view. So let's have a look at how it works, what's inside here. So that's the power lead. That's when the mains 230 volts comes into transformer, and a transformer is a first thing that wouldn't pass modern standards, because as you can see, the windings are one over the other. So the high voltage winding is outside of the low voltage winding. Current safety standards require two windings to be separate, so they're on the same core, transformer core, but they need to be separate. They cannot, the wires cannot physically be in contact. And here is a voltage, AC voltage that is dropped down, goes then through this element that is a thermal controller. So if the current, there is a resistive current, resistive wire here, and when the current drawn by the system exceeds a certain limit, I'm being told by the sources from the internet that it was 5 amps. So if the current flowing through this resistive wire exceeds 5 amps, this works like a bimetal, and then basically faults away from the contact here, and the contact is being lost. So that's the, we can say thermal fuse here. It's actually quite clever, clever way of doing it. Obviously it's not reliable, or not as reliable as modern thermal switches, but it's probably good enough for what this was used for. Then we have AC voltage, AC current coming out here. The current also goes into this selenium rectifier bridge. That gives away a little bit age of this design, because selenium bridges were invented in 1933, and rectifiers were replaced by the more modern silicon ones in the 1960s. So that is likely to come from 1950s, 1960s. Rectified DC current from this point goes into this contacts. It says 12 volts here, and then if we wanted obviously to regulate the speed of the model railway, of the engine that was on the tracks, so here we have a variable resistor. You can see the resistive wire here, and there is a contact going over the wire. I'm not sure if this is going to be clearly visible, but when I turn it, it is the contact goes over this wire here. The total resistance is 52 ohms. So the resistance goes from 0 to 52, and then the output of the regulated current or voltage is available at this contact. I'm saying current or voltage because it could work as a, you can see here, low resistance or high resistance. Low resistance was basically a resistor in series with one of those wires. So the resistance on one of the wires would change from 0 to 52. If we switch this to the high resistance, it would, this essentially potentiometer would work exactly as a voltage divider. So it would create it would connect one of the wires to the middle pole of the resistor, and the other was grounded, and basically would have a voltage divider that would be different. That would be voltage regulated from, I guess, well, 0 to when it was connected all the way down to the ground to the 12 volts if it was in the middle position. So that's essentially how all the electrics works. You can see that there is no isolation here between the high voltage and the low voltage side. Right now there is a need to actually galvanic isolation of the circuit. All these wires can get in touch with one another because they are in the same enclosure. There is just the paper isolation that's isolates the transformer base from the metal casing. So, as I said, a little bit of a safety nightmare, but that's what children were using in the 1950s, 1960s, and I'm not sure if there was a significantly higher number of electrical fatalities than it is right now. Well, maybe because it was quite expensive toy, I guess, at that time, and not everybody could afford it. So maybe there was less popular than it is currently. But anyway, that's how this H&M Clipper power control unit works. Quite simple. I'm not sure what I'm going to do with it. I have no use to it. Potentially useful part is this rheostat, but it's quite low power. It says 1 amp here, so it's not terribly useful. Still more power available than with the current modern potentiometers that usually would tolerate only a few dozens of milliamps. If we are not too afraid of this transformer can be used. This is quite interesting. This thermal switch. This selenium rectifier bridge is probably only useful for the as a piece of museum kit, as a sort of like curiosity. And then contacts, I don't think there is much of use for them. Right, and I'm obviously the main reason why I got it is for the casing. I'm going to repurpose the casing because I really like this hammered paint metal cases. I'm going to put some of my electronic projects into it. Electrical diagram can be found online on the page scottpages.net. There is a description of this, and here it is how it looks like, how the electrical diagram looks like. So this is the transformer, this is the thermal switch, this is the selenium bridge. Here we have the AC output, here we have DC, unregulated DC output, and here is this potentiometer, this big piece with a knob, where we can decide what's the output here on the contacts, and here is either we connect it in series or we have a voltage divider arrangement.